Hello everyone. Topic is numbers. Numbers are mathematical objects used to represent quantities, measurements, or values. They provide a way to quantify and compare things in the world around us. Numbers can be classified into different types based on their properties and characteristics. The main types of numbers include natural numbers. These are the counting numbers. You should remember the term counting numbers. Natural number are the counting numbers. We start we start counting from 1, 2, 3, so on. So these are the natural number. These are the counting numbers starting from 1 and counting indefinitely. Okay. So don't forget, natural numbers are nothing but counting numbers. Any item we count from 1, 2, 3, etc. Okay. Whole numbers. This includes all the natural numbers along with 0. So, whole number is the natural number plus 0. Right? This is whole number. This is whole number. So, all natural numbers are whole numbers, but all whole numbers are not natural numbers. Okay. Exception is 0. 0 is a whole number, but not a natural number. Right. Now come to the integers. Integers include all the whole numbers along with their negative counterparts and 0. Okay. Integer means plus minus as well as 0 are the integer. Plus minus numbers as well as 0. So we can write integers like 0 plus minus 1 plus minus 2 plus minus 3 dot dot dot. These are the integers. Right. Next come to the rational numbers. These are numbers that can be expressed as the ratio of two integers where the denominator is not zero. Rational numbers can be represented as fractions. Example, 1 by 2 minus 3 by 4, 5 by 7. Look here, the numerator and denominator all are integers, but denominator is not equal to 0. Then the number is known as rational number. So, 0 is an rational number because 0 can be represented as 0 by 2 or 0 by any number equals to 0. So 0 is a rational number. Okay. Here the denominator is not equal to 0. Now, irrational numbers. These are numbers that cannot be expressed as a ratio of two integers. Irrational numbers have non-repeating, mind it, non-repeating, non-terminating decimal representation. So, irrational numbers are non-repeating, non-terminating. Example of irrational number are root 2, pi, etc. Okay. If we find out the value of root 2, then we will get this is a non-repeating number and non-terminating number. Real number. It may be noted here, pi is a irrational number, but the value of pi, we all know that pi equal to 22 by 7. 22 by 7 is a rational number. Because it is the ratio of two integers and the denominator is not equal to 0. Whereas pi is a rational number. Look it very carefully and memorize this thing. Pi is the rational number, whereas 22 by 7 is not a rational number, is not a irrational number, it is a rational number, right? Real numbers. Real numbers include all rational and irrational numbers. They represent all possible points on the number line and can be positive, negative, or zero. These are the real numbers. Real numbers are those which can be possible to represent on the number line. Root 2. How do we represent it on number line? This is 1 unit and this is 1 unit, right? And this is right angle. Then this will be root 2 using Pythagorean theorem. So, if this is the number line, okay, and it is 0, it is 1, it is 2, then if we take the line segment as a radius of a circle, then we can draw an arc and we get this in between 1 and 2. This is the point root 1. Similarly, root 3, root 4, root 5 can be represented on the number line. Root 2 is an irrational number, but it can be represented on the number line. Rational numbers, you know, 1 is a rational number, 2 is a rational number, whereas 1, 2 are also whole number, right? And negative numbers, if this side is positive, then this side is negative. Negative numbers, that is integers, are also can be represented on number line. So all these are real numbers. Natural numbers, whole numbers, integers, rational numbers, irrational numbers, all are real numbers. But complex numbers that can be expressed in the form of a plus bi, where a and b are real numbers and I is the imaginary unit. I equals to root over of minus 1. Then this is known as complex number, right? Complex numbers have both a real part and an imaginary. I is the imaginary part, right? These types of numbers form the foundation of mathematics and are used in various fields, including arithmetic, algebra, geometry, calculus, and beyond. They provide a framework for understanding and analyzing quantities, patterns, and relationships in the world. Now come to the basic point, odd and even numbers. Odd and even numbers are classifications of integers based on their divisibility by 2. An even number is an integer that is divisible by 2 without leaving a remainder. In other words, when an even number is divided by 2, the result is an integer. Examples of even numbers include 2, 4, 6, 8, so on. We can identify any number, either it is even or not, by seeing the first digit of a number. If the first digit of a number is either 0 or 2 or 4 or 6 or 8, then this number is even number. Suppose, for example, we take 1, 2, 5, 7. For this number, 7 is the unit digit. It is not equal to 0, 2, 4, 6, 8. So it is an odd number. Take another number, 5, 7, 6, 1, 8. The first digit or unit digit of this number is 8. 8 is even, so the number is even number. Okay. 0 is also an even number. Let another number be 2170. Then the unit digit of this number is 0. So it is also an even number. Other than even number, all whole numbers or all integers are odd numbers. An odd number is an integer that is not divisible by 2 without leaving a remainder. In other words, when an odd number is divided by 2, the result is not an integer. Examples of odd number include 1, 3, 5, 7, 9, so on. Odd numbers are characterized by ending in 1, 3, 5, 7, 9. Here I told even number characterized by the unit digit of any number if fall on these numbers, then the number is even number. Similarly, any number ending with 1, 3, 5, 7, 9, which are not in this series, then the number is odd number. Okay. Any number ending with 1357, any number ending with or in 13579, then the number is an odd number, right? Properties of odd and even numbers. Adding or subtracting an even number to or from another even number always result in an even number. Take an example. 18 minus, suppose, 6. These two are even number. Then the result will be a even number. 12 is also an even number. If we add these two even numbers, then we get the result as an even number. Right? 24 is an even number. This is the explanation. Adding or subtracting an odd number to and from another odd number always result in an even number. If the two numbers are odd number, then the result will be even number. These two are even number. These two are also even number. Right? Adding an even number to an odd number or subtracting an odd number from an even number always result in an odd number. Right? 32 minus, suppose, 13 equals to 90. 32 plus 13 equals to 11. These are odd numbers. Right? Odd and even numbers are fundamental concepts in arithmetic and are used in various mathematical operations and problem-solving scenarios. Now come to the recurring numbers, which is also known as repeating or recurring decimals, are numbers in decimal form where one or more digits repeat infinitely after a certain point. Consider the fraction 1 by 3. When expressed in decimal form, it becomes 0.3333 where the digit 3 repeats infinitely. This is denoted as 0.3 bar. So 1 by 3. So it will be continued and it may be written as 0.3. 0.3 is the 3 is repeating here after decimal number. But digit 3 repeats infinitely. This is denoted as 0.3 bar. Another example is the fraction 5 by 11 in which decimal form is 0.45. Look, 454545 repeating two digits together. This is denoted as 0.45 bar. Okay. Recurring numbers can have one or more repeating digits, and the repetition can start at any position after the decimal point. These numbers can be represented using a bar notation to indicate the repeating part. Okay. Recurring numbers are an important concept in mathematics and can arise when dealing with fractions, especially those that cannot be expressed as terminating decimals. They have applications in various fields, including algebra, calculus, and number theory. Terminating number. Terminating, you know the English word which has end, like as 2 by 5. If I divided 2 by 5, then what we get? So this division ended at 4. So it is a terminating number. In other words, a terminating decimal has a finite number of digits after the decimal point. After decimal, there is only one digit. The fraction 1 by 2 can be represented as 0.5 in decimal form. Here the decimal terminates after the digit 5. The fraction 3 by 4 can be represented as 0.75 in the decimal form. Here the decimal terminates after the digit 75. In contrast to terminating decimals, recurring decimals have digits that repeat infinitely after the decimal point. Terminating decimals are characteristics of rational numbers, meaning they can be expressed as a fraction of two integers. Terminating numbers are relatively straightforward to work within arithmetic and are common in everyday calculations. They are used in various contexts, from simple calculation in mathematics to measurements in science and engineering. Converting a recurring decimal, also known as a repeating decimal, into a rational number involves understanding the pattern of repetition and expressing it as a fraction. Here, I am going to discuss about how a recurring number is expressed as rational number. How we go from this to this. Okay. This will be 3 by 9. 3 by 9 means 1 by 3. How many recurring digits are there? We have to count and put 9 accordingly. If there are 2 digits, then we have to put 2 9. If 3 digits under recurring, then we have to put 3 9. And on the above, that is in numerator, we have to put the number, the whole number. And if there is no digit under recurring, then this should be subtracted. Then the rational number we get. Okay. This will be illustrated in two methods here. Look it. Here is a general process to convert a recurring decimal into a rational number. Identify the repeating pattern. Look for the repeating sequence of digits in the decimal expansion. This recurring pattern will continue indefinitely after the decimal point. Let x be the recurring decimal. Write it as x equal to point ABCD dot dot dot, where ABCD represent the repeating pattern. Count the number of digits in the repeating pattern. Let this number be denoted as n. Here ABCD repeating, so the number of digits repeats 4 numbers. So here n equal to 4. Multiply both sides of the equation by 10 to the power n. When n equal to 4, then it will be 10 to the power 4. To eliminate the repeating decimal, this result in 10 to the power n into x equal to ABCD dot ABCD, right? After that, subtract the original equation from the equation obtained in step 4. So we have to subtract in step 2 from step 4. to eliminate the recurring part. Then what will happen? 10 to the power n into x minus x equal to abcd dot abcd dot minus point abc dot. Okay. It implies that 10 to the power n minus 1 into x equal to abcd. So x equal to abcd divided by 10 to the power n minus 1. Simplify the fraction if possible. If there is common prime factor, then this should be eliminated and get the simplified form. If the numerator and numerator share any common factors, divide both by their greatest common divisor to express the fraction in its simplest form. This process converts the recurring decimal into a rational number expressed as a fraction. The denominator of the fraction will be of the form 10 to the power n minus 1, where n is the number of digits in the repeating pattern. Now, let's illustrate this process with an example. Consider the recurring decimal is 0.636363, right? So, this 2 digit is repeating. So, here x equal to eto 0.6363 dot and 2 digit repeating. So, n is equal to 2. Therefore, this should be multiplied by 10 to the power 2, that is 100, to eliminate the recurring decimal. Then what we will get? X equal to this. So 100x equal to 63.66. 63.6363 dot. Right. Subtract the original equation. 100x minus x equal to 63.63 dot minus 0.6363. So the recurring part is eliminated by subtraction, and we get 100 minus 1 into x equal to 63, that is equal to 99x equals to 63. So here we see the common factor is 9. If we eliminate 9, then we get x equal to 7 by 11. So the rational representation of the recurring decimal 0.636363 dot is 7 by 11. Understand? Let's convert a recurring decimal into a rational number using an arithmetic process, specifically long division. It is the alternative process. Write the recurring decimal as x, multiply x by 10 to the power n, where n is the number of digits in the repeating pattern. So, to shift the decimal point, subtract the original x from the result obtained in step 2. Write the result of step 3 over the repeating pattern. Simplify the fraction if necessary. We have taken similar number and do step by step the process and ultimately get the same result, 7 by 11. Right? So now you are confident enough to find out the decimal number, find out the rational number from a recurring number process. Okay. You are all understand what is number, what are the types of numbers, odd and even numbers, their properties, recurring numbers, repeating, terminating numbers, and the conversion of recurring decimal to rational number. Okay. Thank you all.